Welcome back. This is 6.4 polar coordinates. Today we're talking about what polar coordinates are, how to find them, and how to discover every single possible way to express a polar coordinate. Then we're going to talk about how to convert back and forth from polar coordinates to the coordinates that you're used to, rectangular coordinates. Now let's start with something that's pretty simple. Let's say I have the points, let's say 1 square root of 3, and I wanted to graph this point 1 square root of 3. Well, I could, as you know, I'd go, and this is straight from algebra. You're pretty familiar with this by this point, I'm pretty sure. You'd go right to the by 1. Let's call this 1, and you'd go for x, and you'd go up. Let's say you go up about square root of 3. Let's say this was this be 1. This would be 2. Square root of 3, I guess, is somewhere right around here. This might be, I guess it's square root of 3. So I'd take these 2 points, put them together, and that gives us this point here. And there we have it. We have the points 1 square root of 3. This is all well and good, but if you're a mathematician, you want something better. You want something that's more reliable and something that's easier to work with, especially when you're dealing with something like this, like a square root of 3. And you know, what if, I mean, because when you're doing this, what you're really trying to do, you're trying to graph something that's 2 away. If you were to make a triangle out of this, you would say, hey, this is a, you might be familiar with this. This is a 1, this is a square root of 3, and this is a 2. The hypotenuse would be 2. We're actually making a 30, 60, 90 triangle. This would be 30, and this is 60 degrees. So we have a 30, 60, 90 triangle, and we have to go, but in order to craft it, it's really confusing. We have to deal with that square root of 3. So mathematicians got together and said, let's find an easier way to do this. And they said, well, what we're doing right now seems really rectangular. We're going to the right, and then we're going up by 90 degrees, and we're connecting those points. We're creating this rectangle-like thing, and we're putting it together like that. So we can just call this, a rectangular coordinate. A rectangular coordinate. Now, what if we wanted to find a coordinate a different way? Well, what we're really trying to do is, what we're really saying is I want to go from this origin point, from the point 0, 0 over wherever it is. We want to go to the right 2. We want to go to the right a distance of 2, and then we're trying to rotate that this many degrees, 60 degrees. So we're going to go 60 degrees. We're going to go 2, and we'll go 60 degrees. Let's say we want to call this point P. What we could say then, at this point, if we wanted to write it in this kind of notation, we could say P is 2 is the radius of 2 at 60 degrees. And that's what we're trying to say here. We're trying to say that we're gonna let's just wrap, instead of trying to do this with going right and left and up, let's try to do this with degrees and with a distance. And you can think about it this way if you wanted to. You can think about it as, say, hey, I've got this point in the center of the world, and we're gonna go some distance out from this point, and then wrap around that point. And you can kind of think of it in such a way, the center point is kind of like, almost like a pole sticking out of the center of the page, and we're wrapping around it like a tether ball would wrap around a pole. And so you can kind of think of it, and that's where this name came from. We thought, well, why don't we just call this a polar coordinate? When we consider it in this way, of a certain distance, a certain radius, and then a certain amount that's been wrapped around the radius, we can call this a polar coordinate. And that's exactly what they did, at least as far as my understanding goes. I think that's why they called it that. And so we can use this and see, okay, this is why this works. This is what they're doing here. Now, if you look at this carefully, though, you'll see, well, there's more than one way to write a polar coordinate. You know, I could write it at 60 degrees. I could write it also in its rate as instead of 60 degrees, I could write it in radians. I could also write this a couple other different ways too. I could write this as P times, the P of 2, and then instead of 60 degrees, I could say 60 degrees plus 360 degrees, for example, because I would wrap away, if I was to do that, if I did 260, like this, and I wrapped all the way around, I'd be at 360 degrees, I'd get to the exact same point again. So that's another way to write it. I could also write P 260 degrees plus 360. I could wrap around again the second time and do plus 360 again. I could do that too. In fact, I could just write this as, P of 2 and then 60 60 degrees plus n times 360 degrees. I could just do that, n times 360 degrees. I could do that. That's fine. And I can say like where n is any just actual natural number. And so that's one way I could legitimately write it. If I was to do this in I should probably make this in blue because that's more helpful. If I was to do this in radian modes, what I would actually say is I could say this is p points equals, or p the point is the number of radians, or the distance it is away from the point. We can call that radians. It's be radians, and then the number of degrees in radians. So this would be some degree theta. This would be some degree theta, and on top of that, I can add some number, some integer times 2 pi. I can do that, and that would be the point. And so we can do that for any one of those. We could also find another way to write this if you wanted to as well. We could write it as, let's see, what else can we do? We can go negative as well. So what would happen if I instead of adding 360 degrees, I added only 180 degrees. What if I said p of 2 and then 60 plus 160? So I did 60 degrees plus 160 degrees. Well, that would be, oh sorry, 180 degrees. That'd be down here. So I started this 2, I started going 2, and then I went 60 degrees, and then I'd go another 180 degrees. That's a halfway around the circle. So I'd end up at this point right here, and that would give me this, which is exactly the opposite of what I want. But hey, what if I said I wanted to go 180 degrees, or 60 plus 180 degrees, and then I wanted to go negative 2. If I did p, let's actually do this in a different color for simplicity. Let's do p, I went negative 2, and then I went 60 degrees plus 180 degrees. Well, I could do that too. If I went here, I went 180 degrees plus 60 degrees. I went all that way, and then I went, and from the origin, instead of going 2, I went negative 2. This would be negative 2 from that point. Oh, that would create the same line. Because instead of going forward, I went backwards. So I could do that too. I could say, in a general form, I could say, and we should probably write this down as well. I could write p, where it's negative the radius, and then we'd say pi, or sorry, theta, plus pi. If we were to have theta and we added pi to that, that would give us the opposite of the angle we're looking for. And then if I went from there, and then I added 2 pi to it, and then I added from there 2 pi, or even better, some number times 2 pi, that would equal the same angle. Because you can think about it this way: if I was to take p and multiply by negative 2, and then 60 degrees plus 180 degrees plus 360 degrees, I can add another, or 2 pi. I can add another 2 pi, I can add another 360 degrees as many times as I want to. So using this kind of notation is another way to write the exact same point. So there's a number of different points, a number of different ways we can write this point. But just so you know, if we want to write every single way we wanted to write a point, we would say first, these are the 2 ways to do it. Down these 2 blue ways. We would first write the points, the number of radians, and then theta plus some number, theta, whatever the theta is, plus n times 2 pi, or we'd write negative radians time, and then theta plus pi plus n times 2 pi. Another way to write this bottom equation, if you really wanted to, you could take out the pi and do the reverse distributive and say p of negative r theta plus, let's say it's pi times, what would that be, 1 plus n times 2, or 2n. That's right, 2n. And you could do that just as easily. 2n. And that would be another way to do it. But you can write it anywhere you like. But that's the point. We can write any point in that sort of way. So let's look at this then. What else can we do with these points? How do we know these points? Is there a way to look at this objectively and try to convert from one way to the other, or one way and back? Let's go back and draw our graph again. If we wanted to go back from polar coordinates and go back, if we want to go from polar coordinates to rectangular coordinates, let's say I had that one method over here. Let's say I had the 2, and we had 60 degrees, and we got all the way to this point right here, and we said, okay, what is the x value and the y value of this? Now we can figure this out pretty simply because this is part of the unit circle, and this is part of indeed a 30, 60, 90. This is indeed part of a 30, 60, 90 triangle. So that's all well and good. But we can find a general way to approach this. So if I was to think about this in the form of a unit circle, well, what would we say? We would say that if I was to say, to look at this in the form of a unit circle, if I were to go 60 degrees at all, if I were to go to 60 degrees, that would get me some value. So give me some value. What would this be? This would actually be the cosine of x. The cosine of x. If I was to go to the x value, if I was to figure out how far we went in x value, we would find the cosine of x and then sine of x. Because remember the y value and the x value is cosine of x, and the y value is cosine of theta and sine of theta. The x value is cosine theta, the y value is sine of theta. So we can go ahead and do that to find, and this would be the x value, this would be the y value. So we can say that that's the cosine of theta and sine theta. The only difference is we can find this radius by doing that. But the difference is the radius itself is a certain distance in and of itself. So we say that this radius, if we have a distance of 2 per se instead of a distance of 1, we can multiply that by the cosine of theta and say this is 2 times the cosine of theta, or r times the cosine of theta. Well, however long this radius is, that's how big this will be. The x coordinate will be. So if the x coordinate is normally, say, 1/2, but the radius itself is twice as big. If the radius itself is 2, then we would say it's 2 times 1/2. Or another way to write this, to simplify it a bit, if this doesn't make any sense, this is the equation we're looking for. It'd be the radius, x equals the radius times cosine of theta, and y equals the radius times, well, it'd be the same thing. We'd have the y value of it, which would be the sine of theta, and we're going to multiply that by however big the triangle is, or however big the radius is. So it'd be the radius times the sine of theta. And so we can do that to convert from one to the other and from back and forth. Another thing we can notice is this is some x value and this is some y value. We know that and this is the radius of our polar coordinate. We know that for example, x squared plus y squared equals the radius squared. So we can think of that too. We would want to write that down as well. That the radius squared equals x squared plus y squared. Now let's say we want to find the tangent of theta. If we want to find the tangent of theta, well, we can do that pretty quickly. In fact, we could say that the tangent of theta, let's say tangent of theta equals the sine of theta over the cosine of theta. We know what the sine of theta is. If we were to do a quick bit of algebra on the y equals, that'd be sine of theta equals, well, that'd be y over r, and then similarly the cosine of theta would be x over r. So we're going to do sine over cosine, we get y over x. So that's also helpful to know. The tangent of theta equals y over x. Great. All right. So that's how we convert. So we just did a few things here. Now we know how to can find any coordinate for a polar coordinate. There's a bunch of different ways to write a polar coordinate. We can find any different way to do that. We could write it as we found out how to convert from one point to the other. So at this point, you really have all the tools you need in order to tackle all of the problems. But from here, it's more of just how can we work it out. So if this all makes sense to you, then great. I guess you're done. But if you want to understand how to work this out in practical problems, let's go and do that now. Let's try example 1 in the exercises. This is example 1. If we have the polar coordinates of a given point, we need to find its rectangular coordinates. So we're given the point 3 and 2 pi over 3. And we're trying to find the rectangular coordinates of this. So remember, this is the radius would then be 3, and theta would be 2 pi over 3. And we can think about this conceptually if you wanted to truly iron it out that way. We have a, well, let's use a different angle. Let's say we have an angle that's 2 pi over 3. This is 2 pi over 3, 2/3 pi. I suppose, yes, this is 2 pi over 3, and we have a distance, we have a radius of 3. And we're trying to figure out what this point is at this point over here. And we've done this before, just in a different kind of way, not specifically with polar coordinates. So we'd know that this is the radius. Well, this is the hypotenuse per se. We can draw a right triangle to figure out the rest. If this is 2 pi over 3 radians, then this distance over here must be pi minus 2 pi over 3, and we can figure out what that is. So it'd be 3 pi over 3 minus 2 pi over 3, which would give us pi over 3. So this right here would be pi over 3. Okay, and so from here we just need to figure out what this point is. We can do that. We can go ahead and do that. I encourage you to try to pause this video and figure out the rest from here. But assuming you've tried it out a little bit, we can look at this pretty simply. So we have a 3. There's 3 in the pi over 3. The next thing to do is to figure out what this x value is and what this y value is. We can do this by, well, let's say the cosine. If we want to use cosine to figure out the x value, remember up here that the x equals the radius times the cosine of theta. So if theta is pi over 3, then x equals 3 times the cosine of pi over 3. And then y would be 3 times the sine of pi over 3. You go ahead and calculate that out, and let's see, the cosine of pi over 3, that'd be 1/2. We're going in the left direction, so that'd be -1/2. Let's see, so that'd be 3 times a -1/2. And over here we'd have pi over 3. That'd be root 3 over 2. So it'd be 3 times root 3 over 2. And I suppose you could have done it just with finding cosine of 2 pi over 3 as well, if you wanted to do that. But this makes more conceptual sense in my head. You can do whatever works well for you. So we have this would work out to x equals -3 over 2, and y equals 3/2 or 3 root 3 over 2. And that's it. So that'd be our answer. So if we want to write it down, we get -3/2 and then 3 root 3 over 2, and that's our answer. Okay, good. Let's go ahead and try problem number 5 then. So it says for exercises 5, it wants us to complete the table. First thing it wants to do is complete the table for the polar equation, and B, plot the corresponding points. So it gives us this, it tells us that the radius equals 3 times the sine of theta. And it wants us to complete the table for the polar equation. Now I won't be able to plot the corresponding points too well in here, but we'll at least complete in this little exercise here, we'll at least complete the table. So if theta is pi over 4, we were given this table. Let's just go ahead and draw it out. Theta, we have r, we have theta is pi over 4, we have theta is pi over 2, we have theta is 5 pi over 6, and we have 4 pi over 3, and we have 2 pi. Great. Okay, and we're trying to find what the radius is. We know the radius is 3 times the sine of theta. We'll just go ahead and plug them in and figure out what we get. So it'd be 3 times, let's see, sine of pi over 4 is square root of 2 over 2, or the square root of 1/2. And so 3 times, it would be 3 times the square root of 2 over 2. Let's actually use that in a different color to show us the answer. So this would be 3 times the square root of 2 over 2. And then for pi over 2, Well, that's the sine of that. That's just 90 degrees. So that'd be 1. So 3 times that would be 3. Let's see, 5 pi divided by 6. That'd be 1/2. The sine of that is 1. The y value of that is 1/2. So 3 times that would be 3/2. Pi. Well, the sine of pi, that's just 180 degrees. The y value would be 0 there. It's not up and down at all. So 3 times that would be 0. So 4 pi divided by 3. 4 pi divided by 3 is, well, that's negative 3 square root of 3 over 2. And so if we have negative 3 square root of 3 over 2 to multiply by 3, that gives us negative 3 times the square root of 3 over 2. Again, we just found the value and multiplied by a 3. And 2 pi, again, there's no, that's 180, that's 360 degrees. It doesn't go up or down at all. So that'd be 0. Is the sign of that would be 0, and 3 times 0 is 0. And that's it, and we're done. If we wanted to go ahead and plot those points, and if you were concerned about doing that, we could say then, if we wanted to build a graph here, we could say, I don't know if this graph will be big enough. We would say, let's see, we would say that at pi over 4, say pi over 4 is roughly there. We would be 3/2 over 2. That'd be 3/2. You know, let's just show that the instead of just plotting all the points and perhaps getting a lot of it wrong, being a little messy, let's go ahead and show what this looks like on our graphing calculator. Now, in my graphing calculator, I want to go ahead and change the mode to polar coordinates in order to make this easier on ourselves. Again, last time we talked about parametric equations. Now we're going to go to polar equations. And so we're going to change the y var to polar. And so let's go ahead and hit our y equals. So it says, again, it puts it in terms of radius already. So if we say our radius is 3 times the sine of theta. Again, I hit that x button, but now it's changing to theta because it knows using polar coordinates. So we say 3 times the sine of theta. If we were to graph that, we would get something like this. So if I was to graph each of these points, so if I were to graph at pi over 2, I'd get 3, and if I was to graph pi, that would give me 0. So pi, or at pi itself, actually this is pi, I get 0. And if I was to graph, let's say 2 pi, that would also be 0. If I was to graph 4 pi over 3, again, that'd be negative 3 over 3/2. So that would be something along the lines of in this direction. And that's I mean, so there you have it. So if we were to graph this accurately, we'd get something kind of like this, kind of like that. And that's it. And you can kind of see, so these values, you can kind of see this is the value at after pi. This is 4 pi divided by 3. You can see that this value is negative, and all these values are negative. So all the values down here would be negative. All values down here would be negative, and that's the reason why, is because it needs to be negative in order to create this circle, and we can see that's what it does. So, and that's exactly what it did. And you can kind of see how it works this way, because again, if we go back to the equation itself, we have 3 times the sine of theta. So our radius is 3 times as large as whatever theta should be. So it's going to go all the way up from 0 to 3, and you're going to make this neat circle here. Great. So that's 5. Number 7 is right below it. So we'll say in exercise 7, it asks us to plot the point with the given polar coordinates. And so we're given this point 3, 4 pi over 3. So let's go ahead and start with the point itself. And what's really neat about this is we don't really need these axes as much anymore. These axes that we use to plot points, and we make tick marks on them, they're not quite as necessary anymore. In fact, we can use a whole different method of graphing them if we wanted to. We'll start at 0, and our first goal is to figure out what direction we're going in. So we'll go 4 pi over 3. Well, 3 pi over 3 would be 180 degrees. 4 pi over 3 is 1/3 beyond that. So we're going in this direction. So this is 180 degrees down here if I wanted to really think about it that way. But I'm going about in this direction, and I'm going in a direction of 3. So I'm going at a distance of 3. So I'm going 3 units in this direction. So that would give me about, if this was 3 units, it would give me that point right there. Whatever that point is, that would be that point. If I wanted to graph if I want to put the axes on, I could as well. But in all honesty, they're not even quite necessary. Again, we don't even need to reference them at all. We can just find the angle, go the distance, and we're done. And that's how you graph a point in that kind of way. So that's 7. 15. 15 says, find the rectangular coordinates of the point with the given polar coordinates. So we're given the points. We're given this. We're given this this polar coordinate. We're given the polar coordinate 1.5, and let's use it in green. We're given the point 1.5, and the coordinate 7 pi over 3. And once we need to first convert this into rectangular coordinates. Is what it's asking us to do. Well, remember again. So we know that x equals the r times the cosine of theta, and y equals r times the sine of theta. So if x is, let's write that again. X equals r times the cosine of theta, and y equals r times the sine of theta. All right. Now we go ahead and just plug these in and figure out what we get. If you have 1.5 as our radius, so we'd have x equals 1.5 times the cosine of 7 pi over 3, and we'd have y equals, let's see, y would equal 1.5 times the sine of 7 pi over 3. And you can go ahead and work that out if you like. If you were to work that out and fully get the answer, the full answer, I could try to work that in my head, but it would be something around the ballpark. Let's see. That'd be something around the ballpark of, I suppose it'd be about 3/4. Yeah, 3/4 would be x, and y, that's a bit different. That'd be more of that'd be 3 times the square root of 3 over 4, and that's what that would be. Yeah. So our full coordinate would be 3/4, and then 3√3 over 4, and that seems about right. Again, these are kind of tough points to plot. It makes it much easier to just use the polar coordinate in these kind of situations. But now you know you can convert from one way to the other. So that's number 15. Number 23. It says it gives us this polar coordinate, and we need to find all of its possible polar coordinates. So it gives us the coordinate where p equals, let's see, 2 and pi over 6. And so there's a couple things we know we can do. Again, we can add pi to it. So remember, if we go all the way to the top, we can remember that you can add a pi. You can add 2 pi to anything and keep it the same. You can also add pi to it and make the radius negative, and then it would stay the same. That's what these two are. And so we can do both those things here. So let's say we have, let's go ahead and write this down then. So we can say it's r. We can go ahead and write it as the radius of 2, and then we can say it's pi over 6 plus some number, any integer. And by integer, I mean any integer. So -3, 2, 5, any number times 2 pi. So that's one way to write it. We could also add pi to this and get a little bit further. And if we did the other way that's one way to write it. Well, that's some of the points. The other points we can write is if we did -2. If we try to go backwards, try to go a certain amount and go backwards from it, we do -2, and then we do pi over 6 plus pi, and then we do after that we can do plus some sort of number times 2 pi. All right, let's go ahead and simplify this pi plus pi over 6. Well, that's 6 pi over 6. Pi equals 6 pi over 6. So it'd be -2 and then 7 pi over 6 plus some number times 2 pi. All right. And then these sections right here, these would be our answer. These are both together, they make all the different possible combinations of ways we can write these coordinates. Alrighty, so that's 23. 27 asks to find the rectangular coordinates of the, it says it gives us these rectangular coordinates, and it finds the polar coordinates of P when theta is a 0. Let's see. A is when theta is less than or equal to 0, and is greater than or equal to 0, but it's also less than or equal to 2 pi. To find the coordinates for B when negative pi is less than or equal to theta, and then theta is less than or equal to pi, and C when 0 is less than or equal to theta, which is less than or equal to 4 pi. All right, so let's go ahead and try to visualize what they're talking about here. We have our circle, and let's do this in different colors. Let's do A in yellow to start with. So A is going to be from 0 to 2 pi. That's just the whole circle. That's just from 0 to just one rotation. One rotation. So this is one rotation. And then on top of this we have B. Let's see. B is from negative pi to pi. So this would be from negative pi all the way to pi. All right. This is also one rotation. And then this would be one rotation. And then this over here would be from C would be from 0 all the way to 2 pi, and then 2 pi again, so 4 pi. So this would be a total of 2 rotations, starting from 0 there. Great. So let's go ahead and work this out. We have our points that they give us, the rectangular points. The point they give us is 1, 1. All right. So if we went and graph this, that would give us, if we were to graph this on some axes, we could say, okay, this would be the point 1, 1. This would be 1 here, 1 here. So we're going to figure out what the radius would have to be. Let's see, that'd be 1 squared plus 1 squared equals the radius squared, and that'd be 2 equals the radius squared. So the square root of 2 equals the radius. You may be familiar with this triangle by now. I hope you are. But here we are. So the radius is 2 pi, is square root of 2. Great. So we now know that there's two different ways to write. Well, there's two different methods of finding polar coordinates, or two different elements probably of writing them all. And the first one is just by adding 360 degrees as many times as we can in order to find them. The other one is by adding 180 degrees and making the radius negative. So from 0 to 2 pi, we've got this point here. So before we even get to that, what is this? This is a 45 degree, 45 degree, 90 degree triangle. So this is the points. If we wanted to write one of the points, that'd be root 2 and then 45 degrees. Okay, so that's one of our points, and that's between 0 and 2 pi. Great. If I wanted to find it again, if I wanted to add 360 degrees to it, well, that wouldn't really help. So A is, at least one of them is root 2, 45 degrees. Okay. If I wanted to add 360 degrees, that'd be 415 degrees. That's beyond 2 pi. That's a bit far. Let's see. So that's beyond our bounds. But let's say we want to do between. But there's another way to do it. So we can't, if we subtracted 360 degrees, we would find another value either. So this is the only way to do it using that first method. And again, remember, there's two ways. Let me write this down. The two methods of finding it are, and then we have theta plus 360 degrees times any number, and then we have negative r, and then we have theta plus 180 degrees, and then plus 360 degrees times any number. All right. So that's one way to write it. And this is the only way we can solve it for that first route. Now, if we went to that second equation, that negative r, we can write a equals let's see, negative square root of 2, and if we added 180 degrees, that would be, let's see, 180 plus 45, that'd be 225 degrees, right? And that would be the way to write it that way. If I added 360 degrees, that'd be beyond 2 pi. If I subtracted 360 degrees, that'd be below 0. So that's about all we can write here. Let's try b. So b says instead of that, let's start with a full rotation for. Let's start at pi, or negative pi, and go all the way to pi. So if I started at negative pi and went all the way to pi, well, I can kind of see that initial value is in that range. So I can go ahead and put that for b. That initial value of square root of 2. Square root of 2, and then 45 degrees. That's in that value. That's between negative pi and pi. Now, if I were to go from there and go all the way down in this direction, if I was to increase down in this direction, well, that'd be going beyond the bounds of it would be passing pi. We don't want to pass pi, so we should go the other direction. So we can still go negative if we wanted to. We could still have that negative root 2, but now we have to go back in the other way. So I could instead of adding 180 degrees, I could potentially just subtract 180 degrees and see what we get. Let's see, if I subtracted 180 degrees, another way to think of that is add 180 degrees and then multiply 360 by negative 1. But either way, I can subtract 180 degrees from 45 degrees. So this would be 145 minus 180 degrees, which would be, what would that be? That'd be 25, it's 67, 35. That sounds about right. Yeah, so it'd be negative 135 degrees. So let's go ahead and write that as negative 135. All right, and that's about all we can do for that one. Now we've got this monster graph that starts at 0, this monster C that starts at 0, and it goes all the way over to 2 pi. So if I was to start off with, it goes off to 4 pi. Now if I was to start off with, well, 45 degrees is between 0 and 4 pi, so I can go ahead and write that. So we have root 2, and then we have 45 degrees. I can add 360 degrees to that, and that'd still be within 4 pi. That'd be 45 degrees plus 2 pi, which is still within 4 pi. Let's see, if I added 2 pi to this, or added 360 degrees to this, this would be, it also equals root 2, and then 45 plus 260, that'd be 375 degrees. And then from here, I can also subtract, but if I added 2 pi again, if I add another 360 degrees, that'd definitely be over 4 pi. So I've already added 2 pi so far. I've added 360 degrees before. So if I added 2 pi again, that'd be 4 pi plus 45 degrees. That's too far. So that's about as far as we can go for this first equation. But we can still do the second equation if we wanted to. The second formula. If I did negative root 2, I can add 180 degrees and get our first point, which is what we have. We've had that before. That's 225 degrees. That's still not even within 2 pi yet, so it's below 2 pi. So I can add 2 pi and get it to be below 4 pi. We can still do that again. So if I added 2 pi to this, or 360 degrees to this, I would get negative root 2, and then 225 plus 360 degrees, that'd be 585 degrees. Right? Yeah, that's what that is. And that's it. And those are all the different ways to write it. So that'd be all of our possible solutions. And this would be our total answer. Great. All right, last one. Let's look at exercise number 33. I think, yeah, so we're going to do 33. And 33 says, 33 says, we have to use our grapher to match the polar equation with its graph. And it gives us r equals 4 times the cosine of 3 times theta. And so it just says, really just put this in your grapher and see what you get. And we can do that. So if we took out our graphing calculator, again, make sure your mode is in polar coordinates instead of radians, or instead of parametric or function notation. We want to make sure we're in polar, so POL for pole. Then we put in over here, we're just going to go ahead and plug this in. We'll say 4 times the cosine of 3, and then I'm going to hit this X button, but because it's in polar, it's going to put theta. We can see that X, T, theta, N. And so we'll put that in there. And when we hit graph, oh, we get this lovely thing. And so that's our answer. That's literally all we have to do. And so on the book, that matches with C. So C would be our answer here. We could just respond with C. All right. Hope that was helpful. And we'll see you next time.